In this video, we describe the basic algorithm of our optimized image morphing technique. We address several challenges. Our optimization technique lets the user specify very few correspondences. To avoid ghosting artifacts, it provides per pixel alignment based on structural similarity. To avoid boundary artifacts during morphing, it ensures that the entire rectangular domain of the image is well defined. Finally, it enables the user to interactively and effectively control the appearance of the morph. Traditional approaches construct a map from one image to the other, but this leaves disoccluded regions undefined. Due to this asymmetry, a reverse map is often necessary, but maintaining consistency requires expensive bookkeeping. We introduce a simpler approach, the halfway parametrization. The idea is to define a vector field V over a domain that is intermediate between the two images. Thus, the intermediate image is parametrized by a single continuous function. We minimize an energy function consisting of three terms: structural similarity between the images, smoothness of the mapping, and deviation from user-specified correspondence terms. We will briefly introduce these terms. For details, please refer to the paper. The similarity energy attempts to match pixel neighborhoods of each halfway image pixel in the two deformed input images. We use a modified structural similarity energy to match regions with similar edge structure, such as the object boundaries in this circle to star example. The UI energy term ensures that user-specified correspondence points are matched. In this example, the center of the circle is mapped to the center of the star, as specified by the red correspondence point. Away from any constraints, the smoothness energy term ensures that the resulting vector field favors affine functions in the mappings to both left and right images. In order to render our morph sequences, we present a novel per pixel iterative algorithm that efficiently determines corresponding halfway image domain points and blends the colors from each input image. One of the challenges faced by the renderer is that a halfway domain pixel P may map outside the bounds of an input image, as shown here. This occurs frequently in examples that involve a panning or a zooming motion such as this one. For such cases, we need plausible color values beyond the image boundaries in order to produce a smooth morph. We propose a technique that extends each image using gradient domain transfer of content from the other image. The correspondence is guided by the previously computed vector field. In this zooming example, the right image can retrieve the two towers beyond its boundary by taking advantage of its computed correspondence to the left image. To rasterize intermediate images, a common approach is to render a triangle mesh that is deformed using the vector field. Our direct pixel evaluation approach does not require the rasterization of a fine triangle mesh, and more importantly, can produce plausible values beyond the boundary of the halfway image, thus filling the entire rectangular domain of all intermediate image frames. When generating the intermediate image, the simplest approach is to assume each pixel follows a linear path. However, in some situations, a linear path may grow or shrink image regions, such as in this example. By using quadratic motion paths, the extra degrees of freedom allow us to globally optimize for motion paths that reduce pixel neighborhood deformations in the intermediate images. Now we'll give a quick real-time demo of our user interface. The two input images are shown at the top. The halfway image and a real-time morph using the current vector field is shown at the bottom. The system automatically recomputes the map every time the user adds, modifies, or deletes a correspondence point. Here we first add a correspondence point to better align one of the eyes. We can enter this correspondence point directly on the halfway image where the artifacts of using the current map are noticeable. The vector field is quickly re-optimized considering this correspondence point. Then we only need one final correspondence point to better align the face. In this case, we further fine-tune the position of the correspondence point in the two input images. The vector field is optimized again, and this is the resulting morph. For further details on the user interface, please refer to the paper. To see detailed animated versions of our morphs and extensions, please refer to our results video in the supplemental material. Thank you for your attention.